Welcome to the Deep Dive. We're the place you come to when you want the really key takeaways pulled out from, well, often a whole lot of information.
Exactly. We sift through it so you don't have to.
And today, we're plunging into artificial intelligence. We've got an introductory lecture transcript, which, okay, sounds maybe a bit basic.
Oh, you might think, intro lecture, how deep can it be?
But hidden inside is this demonstration, this moment that really hints at some massive shifts underway. Things you might not expect from just, foundational stuff.
And we're not stopping there. We're also going that extra mile, looking at some really, really cutting-edge ideas that are pushing the boundaries of AI right now.
So yeah, two main parts today. We'll start with something pretty concrete, this demonstration showing how fast things are moving.
And then we'll zoom out a bit, look at some more, let's say, theoretical frontiers, but ones that are incredibly exciting.
Okay, let's dive in. Part one, this first insight from the transcript. What really jumped out at me was this demonstration bit. It highlighted this almost unbelievable compression, the shrinking of time and resources needed for, well, pretty complex generative AI stuff.
Yeah, the contrast they drew was stark, wasn't it?
Totally. Think back like maybe 5 years ago. If you wanted a realistic video, 2 minutes long, of someone talking,
Yeah.
maybe not even a real person, that was a massive undertaking.
Yeah.
Weeks of data gathering, maybe $15,000 in compute time alone.
A huge investment.
Yeah, and you were pretty much locked into whatever script you fed it beforehand. No real interaction.
That baseline really sets the stage. It shows just how constrained things were, relatively speaking, the resources, the inflexibility.
Exactly. Because then the lecture demonstrates that now, today, you can take just a few minutes of someone's audio
Just minutes.
and create a convincing voice clone almost instantly.
Right.
And not just a static clone reading a script.
Right.
This clone voice can then have a dynamic, totally unscripted conversation.
That leap is, well, it's kind of staggering when you put it side by side like that.
It really is.
Yeah.
Weeks and thousands of dollars down to minutes and, immediate interactive results. That's not just making it a bit faster or cheaper.
No, it feels different. It's a fundamental shift, like you said.
Yeah.
Speed, ease of use, the interactivity. It opens up completely new possibilities.
We've gone from these huge kind of rigid pre-planned projects to something you can spin up immediately, something flexible.
So the big question becomes, what does this mean for what's possible now? And maybe even more, how fast are things going to keep changing?
Right, and it makes you think progress isn't always that slow, steady climb we imagine. Sometimes it's these sudden jumps.
Absolutely. Capabilities that seemed way off in the future suddenly just arrive. And the Insight Impact Score, we assign this, 9.20, reflects that.
Yeah, 9.20. It's high because it's not just that the tech exists, right?
Exactly. It's how accessible it's become, how quickly you can use it. That ease is the unlock. And maybe not everyone's quite internalized what that means yet. Think about, say, voice acting, custom audio. This changes things.
Definitely. And, for you listening, if you really want to feel this change, maybe try out one of the current AI voice tools, like 11 Labs or Play.ht. There are a few. If you're comfortable with their terms, just record a short bit of your own voice. See how fast it can create a synthesis. It really gives you that tangible, firsthand sense of this acceleration. It's quite something.
Okay, so that's the wow factor of the current capabilities.
Yeah.
But let's shift gears a bit. Let's look underneath the hood.
But what makes these advancements possible?
The transcript also touched on something more fundamental. How these deep learning models actually learn. And this idea of a hierarchy of features is key.
Hierarchy of features. Okay, it sounds a little jargony. Can we break that down? The lecture used facial recognition, which I found helpful.
Yeah, absolutely. Think about recognizing a face. Your brain doesn't just see face instantly, right? It likely builds it up.
Okay.
It probably starts with simple things like detecting basic lines, edges, maybe patches of color. Then it combines those into slightly more complex shapes. Circles, ovals, curves.
Makes sense.
Those shapes then start forming features, eyes, a nose, a mouth, and finally, putting all those features together in the right arrangement gives you the complete face you recognize.
So layers of complexity.
Exactly. Now, the old way of doing AI, traditional programming, would mean a human programmer had to sit down and explicitly tell the computer every single step.
Like, look for 2 circles. Now look for a line below them, like a very detailed recipe.
Precisely. Step-by-step instructions, all defined by humans. The breakthrough with deep learning is, Well, it's quite different.
How so?
You show these models millions, billions of examples, in this case, faces. And the models, through processing all that data, learn to identify these layers, these hierarchical features on their own.
Wait, on their own, they figure out the steps.
Yes. They discover that the most efficient way to identify a face is to first look for edges, then shapes, then parts, then the whole configuration. They automatically find this optimal, layered structure, this hierarchy. We don't explicitly program each stage.
Wow, okay. That is a big difference.
Yeah.
The AI isn't just following the recipe. It's kind of writing the recipe itself based on the ingredients it sees.
That's a great way to put it. The automatic discovery of the hierarchy. That's the core insight here. And the practical upshot is huge. It means the AI gets much better at generalization, recognizing faces it's never encountered before because it's learned the fundamental building blocks, not just specific examples.
That makes sense why the Insight Impact score here is 7.50. It's foundational, maybe not as immediately flashy as the instant voice cloning,
Right.
but is absolutely crucial for understanding how that flashiness even happens. It underpins everything.
It really does. It's the engine driving a lot of the complexity we're seeing. And for you, the listener, if you want to sort of simulate this, try a little mental exercise. Look at something visually complex around you. A busy street, maybe your desk, a bookshelf. Consciously try to break down what you see. Start with the absolute basics: lines, colors, simple shapes. Then mentally build up objects, groups of objects, the overall scene.
Like actively noticing the steps my brain usually does automatically.
Exactly. It's obviously a vast simplification, but it gives you a little taste of that hierarchical processing that these deep learning models learn to do so effectively and automatically.
Interesting exercise. Okay, so we've seen the rapid progress and a key reason behind it. Now let's shift again into these extra mile insights, more cutting edge stuff.
Right, moving towards the research frontier now.
The first one that really grabbed me was this idea,
Yeah.
this potential for what's being called System 2 reasoning emerging in large AI models. What exactly is System 1 versus System 2?
Okay, so this comes from psychology, thinking about how we think. System 1 is our fast, intuitive, automatic thinking. Pattern recognition, gut feelings, quick judgments, like recognizing a friend's face instantly.
Got it. Effortless thinking.
Pretty much. System 2 is the slower, more deliberate, effortful kind of thinking. Logic, step-by-step reasoning, planning, complex calculations, like solving a math problem or carefully considering a major decision.
Okay, so AI is good at System 1. Pattern matching, generating fluent text. That sounds right.
Extremely good. That's where much of the progress has been. The really surprising thing, though, the frontier insight, is that as we build these AI models bigger and bigger,
Scaling them up.
yeah, scaling them up and feeding them incredibly diverse, massive data sets, text, code, scientific papers, everything, data sets that implicitly contain examples of reasoning. These models are starting to show signs, maybe just hints for now, but signs of unprogrammed System 2 capabilities.
Unprogrammed. So we didn't explicitly build in logical deduction rule.
Not in the traditional sense. They seem to be able to perform multi-step reasoning, planning, problem solving in ways that weren't directly coded. It's like it's emerging.
So it's not just sophisticated memorization or pattern blending from the training data.
Well, that's the billion-dollar question, isn't it? The hypothesis, the exciting possibility, is that this might be the emergence of genuine reasoning, even if nascent, simply arising from the sheer scale of the model and the richness of the data.
Wow.
It really challenges how we think intelligence might arise. Maybe complex reasoning isn't something you have to explicitly design, but something that can potentially crystallize out of enough data and computation.
That's mind-bending. The Insight Impact score reflects that, doesn't it? 9.99.
Absolutely, 9.99. Because it's right at the edge, highly debated, and the implications are profound if it holds true. Could scaling just keep unlocking qualitatively new abilities? We don't know yet.
It makes you fundamentally question what intelligence is. And for the listener, the suggestion to explore this is fascinating.
Yeah.
Try a complex logic puzzle yourself. Really track your own steps.
Yeah, be conscious of your system too.
Then give the same puzzle to one of these big AI models like a GPT-4 or Claude and ask it to think out loud to explain its reasoning step by step.
Comparing its process, its potential missteps or insights to your own, that could be really illuminating about the nature of this potential emergent reasoning.
Definitely something to try. Okay, next frontier insight. This one kind of flips the classic AI problem on its head. The curse of dimensionality.
Ah, yes, a long-standing challenge. Traditionally, in machine learning, having too many variables, too many dimensions in your data was seen as a bad thing.
Why was that?
It makes it much harder to find patterns. The data becomes sparse, distances between points become less meaningful, it just gets computationally difficult and requires exponentially more data to cover the space. That was the curse.
Okay, sounds like a real problem. So what's changed?
What's changed is the rise of modern self-supervised learning. This is where the AI learns from unlabeled data, often by setting itself prediction tasks, like predicting the next word in a sentence or predicting a masked out patch in an image.
Learning without direct human labels for everything.
Exactly. And in this context, incredibly high-dimensional input, think about the raw pixels of every frame in a video, or just vast streams of text. This massive dimensionality is actually becoming an advantage.
Wait, the curse becomes a blessing. How? That sounds totally counterintuitive.
It does. But the idea is that this immense, continuous stream of high-dimensional, complex data gives the AI the raw material to build incredibly rich, detailed internal representations of the world.
Internal representations, like models of how things work.
Precisely, these world models.
Hmm.
By processing, say, countless hours of video, the AI isn't just learning to recognize objects. It starts to learn implicit physics, cause and effect, how objects interact, the consequences of actions, all the subtle rules governing reality that are embedded in that high-dimensional data stream.
So it's learning the underlying structure of the world from the sheer complexity of the input.
That's the idea. Think about models like OpenAI's Sora, generating those incredibly realistic video clips, or large multimodal models that understand connections between images, text, and sound. They seem to be developing this deeper, grounded understanding by grappling with the complexity, not despite it.
So more complex data isn't just more examples, it's richer raw material for learning fundamental truths.
Exactly. It allows the model to build a more foundational understanding, which is why this also gets that 9.99 Insight Impact score. It's a paradigm shift in how we view data complexity. It suggests the path to more general AI might involve embracing this complexity, not simplifying it away.
It's like meeting the full, messy reality to learn how reality works. For the listener, the suggested exercise is quite clever too. Watch a short video, completely silent, of simple physical interaction. Maybe a ball bouncing, someone stacking blocks and knocking them over.
Something basic.
And then consciously try to list out all the unspoken rules, the physics, the expectations you have about how those things should behave. Gravity, momentum, object permanence, solidity.
You quickly realize how much knowledge is implicit even in the simplest scene.
Right, and that's the kind of richness the AI is potentially extracting from that high-dimensional video data. It highlights the sheer complexity of the understanding needed.
Yeah, it's a good way to appreciate the learning task. Okay, final frontier insight. This one tackles a known inefficiency.
Which is?
Current AI, especially deep learning, is incredibly data hungry compared to biological learning. A human child learns about the world with vastly less explicit data than today's models need.
Right, we learn concepts incredibly quickly sometimes.
Exactly. So the question is why? And a leading idea focuses on biological anchoring and inductive biases.
Inductive biases, and we touched on this. It sounds like built-in assumptions are starting points.
That's a good way to think about it. The hypothesis is that biological intelligence doesn't start from a completely blank slate. We seem to come equipped with certain fundamental priors, certain built-in assumptions about how the world works.
Like what?
Things like the concept of distinct objects, the idea of agency, that some things act intentionally, basic notions of cause and effect, spatial reasoning, maybe even a rudimentary understanding of physics. These are the inductive biases.
So things we seem to know or learn incredibly fast without needing millions of examples.
Precisely. And the frontier idea here is that the next big leap in AI efficiency, and crucially, its ability to generalize its learning to truly new situations, might come from figuring out how to embed these core biological priors deeply into the AI's architecture.
So it's not just about copying the brain structure, like neural networks sort of do.
No, it's deeper than that. It's about identifying and implementing the fundamental learning principles or starting assumptions that make biological learning so powerful and efficient, giving the AI a better head start, a better framework for making sense of the data.
Building in some foundational understanding of how the world generally works.
You could put it that way. It's an incredibly hard problem, of course. It sits right at the intersection of AI, neuroscience, cognitive science, which is why it also gets that 9.999 Insight Impact score. It's a grand challenge.
Trying to distill the secret sauce of biological learning efficiency.
Yeah.
And the suggested thought exercise for the listener.
Observe a young child learning something new. how they interact with blocks, learn shapes, figure out how a toy works.
Uh-huh.
Notice how quickly they often grasp underlying principles from just a few examples. They experiment, they generalize, reflect on what built-in knowledge or learning strategies they seem to be leveraging that current AI often lacks, needing massive data to approximate.
It really highlights the difference in learning efficiency.
It
Fascinating.
really is.
Well, this has been quite a journey. We started with that very tangible, almost startling acceleration in what generative AI can do right now.
That instant voice cloning example really brought it home.
Yeah. And then we looked under the hood at that automatic learning of hierarchies and deep learning.
The foundational engine enabling that progress.
And then we leaped to the absolute cutting edge, these frontier ideas. Emergent System 2 reasoning.
The potential for intelligence arising from scale.
The curse of dimensionality becoming a blessing. Using complexity to build world models.
Turning a problem into an advantage.
And finally, looking to biology for clues on how to build AI that learns more efficiently with better inductive biases.
From the demonstrable present to the speculative but incredibly exciting future.
So as we wrap up, here's something for you, the listener, to really chew on. Thinking about all these advancements, the speed, the potential for emergent abilities, the drive towards more efficient, perhaps biologically inspired, learning, what truly fundamental shifts do you anticipate? How might our interaction with intelligence, maybe even our understanding of what intelligence is, change in the coming years?
It's moving so fast. The questions are getting bigger and bigger.
They really are. Keep exploring, keep thinking about the implications. It's definitely one of the most fascinating and rapidly evolving fields out there right now.